Good morning, everyone. We're going to pick back up here in chapter 11 at the end of our slides. We'll pick back up on the slide that we were looking at last time. We have just a few more slides in chapter 11 before we'll get to some of the chapter 10 review. I put up a second review packet for chapter 10. We'll probably get through both of those here today. So if you're looking for the problems that'll follow the chapter 11 notes, look for in the lecture slides, the chapter 10 lecture review problems. So let's remind ourselves that vapor pressure is the one property that goes inverse to intermolecular forces. So our vapor pressure is inversely proportional to strengths of intermolecular force. If you strengthen the intermolecular force in a substance, the molecule is going to hold on to itself and not release the molecule into the gas phase as readily. It's going to take a higher temperature for the sample to have enough kinetic energy to break free of those intermolecular forces. And so that's going to serve to reduce the vapor pressure. So compounds with strong intermolecular forces have low vapor pressures. And then inversely, if you have weak intermolecular forces, you have a higher vapor pressure. And then temperature has a relationship that vapor pressure is directly proportional to temperature. Temperature is directly a measure of average kinetic energy. So as you increase the temperature of any sample, you increase the energy given to the molecules, you increase their velocities, and then you're going to give the molecules more energy to break free of those intermolecular forces. And so at higher temperature, we have a higher vapor pressure. And so let's take a look at the intermolecular force comparison again. So the molecules we're comparing here are diethyl ether. That's a relatively weaker compound in terms of intermolecular forces because it does not hydrogen bond. So you have no H bonding here. Ethyl alcohol forms one hydrogen bond. Water forms the two hydrogen bonds. And then ethylene glycol has that second hydroxyl group. It's kind of like a dialcohol or a diol. So it has two hydroxyl groups, has that second hydrogen bond, also then adds some dispersion force. And so if we look at any particular temperature, let's look around room temperature, we can see that the weaker compound has the higher vapor pressure. So if we're around 25 degrees C for diethyl ether, it has a pretty high vapor pressure. If we then go to ethanol, then has a lower vapor pressure, stronger intermolecular forces. Water, even stronger intermolecular forces, even lower vapor pressure. And then ethylene glycol probably wouldn't even have any discernible vapor pressure at room temperature, or so around 25 degrees C, your ethylene glycol is pretty much zero vapor pressure. And as soon as we start increasing the temperature of any of these samples, we notice that the vapor pressure increases. The point at which our vapor pressure equals our standard atmospheric pressure is what we call that standard or normal boiling point. So our standard or normal is another word to call this. Boiling point is just the point at which the sample has a vapor pressure that's equal to the surrounding atmospheric pressure. So standard atmospheric pressure, 760 millimeters of mercury. So the boiling point's defined at the point at which the sample has a vapor pressure of 760 millimeters of mercury. And one of the things that's interesting is you can change the boiling point of a substance just by changing the surrounding pressure. There's two easy ways to do this. One is either through the use of a vacuum pump. So if you put a vacuum onto a sample, you lower the surrounding pressure. So let's say we lower the surrounding pressure either in our room, that's gonna be a little bit harder, but in a sample through using a vacuum pump, let's say we can reduce the pressure down to 200 millimeters of mercury. So then at that point, the diethyl ether would boil at around 0 degrees C. Our ethanol will boil at about, probably about 45 degrees C. And then water would be boiling at about 65 degrees C. So you can lower the boiling point of a substance by applying a vacuum and reducing the surrounding pressure. If you go up in the mountains where the surrounding pressure is lower, so at high elevation, you probably noticed this either if you've been camping in the mountains or if you just looked on directions of some different foods. It says at high elevation, you generally need to cook food longer because if you're like boiling a pot of pasta, you're expecting the water to be 100 degrees C to cook the pasta. If it's really a lower pressure, say you're around here and your water temperature is only 90, 95 degrees C where it's boiling, it's going to take longer to cook the pasta because the water's just not as hot. So at lower pressure, we have a lower boiling point. So our boiling point trend for water, or comparison of rank ordering the boiling points of water at high pressure versus low pressure, our low pressure will have the lowest boiling point, then standard pressure, and then we can also apply a pressure Probably the most common way that you've seen an applied pressure increase the boiling point of a substance is a pressure cooker, which is an instant pot. So if you've ever used an instant pot under the high pressure setting, you're just sealing in the cooker, and then it's allowing the pressure to increase from the vapor pressure of water being given off, increasing the pressure. And so if you go to a higher pressure, then you can have water boil at a temperature more like 110, 115 degrees C instead of 100 degrees C. So food will cook faster because water is just hotter. And so we increase our boiling point at high pressure. So I just wanted to kind of see that we can control boiling point. It's just a factor of the surrounding pressure. And I like to think of this as pretty neat that there's like an inward force holding the molecules together, and then there's also like a downward force of gravity holding the liquid together. And as soon as that inward force is weaker than gravity, then the sample just turns into a gas and it goes into the gas phase. So as soon as your vapor pressure goes beyond, the pressure of expanding the gas goes beyond atmospheric pressure, then you have the spontaneous boiling of your liquid. So let's rank order here, or just predict which substance has the highest versus lowest. If we can rank order too, that'd be great. But take a second here to look through the choices and think which of these compounds you think has the highest versus the lowest vapor pressure at a given temperature. So you may have been spotting that there's the key difference here, how many different hydrogen bonds these substances can make. Ethanol, just one. Ethylene glycol, like we mentioned earlier, has two. Glycerol has a third. It has even a longer carbon chain and also picks up a third hydrogen bonding site. It has 3 alcohol groups within it. And then, of course, pentane has 0. So which of those has the weakest intermolecular force? That would be pentane. So pentane, having no hydrogen bonds, relatively similar size. If we look at its size compared to maybe like glycerol, it's pretty comparably sized in terms of its molar mass to something like glycerol. We want to be careful sometimes comparing molecules. We don't want to compare like a very large hydrocarbon that has no hydrogen bonding to a very small molecule of hydrogen bonds. That might be a tricky comparison to make. But pentane here would seem like it's going to have the highest vapor pressure because it has no hydrogen bonding. It's not tremendously larger than any of the molecules here, so it seems like this one here should have the highest vapor pressure because it has the weakest intermolecular force due to having that 0 hydrogen bonds. And then, of course, the inverse, the strongest intermolecular force should be the one that has 3 hydrogen bonds, and also it's also the largest overall. It picks up an extra like CH group on it, so have a little bit more dispersion force. So glycerol should be the best. So this should have the lowest vapor pressure and the strongest intermolecular force. So we'd expect the glycerol with the 3 hydrogen bonds to have the highest boiling point. At a given temperature, the lowest vapor pressure. We'd expect that it would have anything that tracks with intermolecular forces to be the highest, like the highest viscosity, the highest surface tension, because those properties are directly proportional to strengths of intermolecular force. So one of the last topics in the chapter is phase diagram. So like a phase diagram shows us under a set of pressure and temperature conditions, do we expect the substance to be a solid, liquid, gas? And we even pick up a new phase that we call the supercritical fluid. And let's talk about the supercritical fluid kind of first, because if we look here, we're looking at pressure versus temperature. And when we get the really high temperatures and pressures, we get to a point where it's pretty hard to classify the substance as a gas or a liquid. And so the supercritical fluid is really just like a gas-liquid hybrid. It's really nothing all that exciting. It's not some like, had a word in my head that I lost. It's not like some crazy state. It's just a substance where you have a hard time calling the substance a gas or a liquid. So you start to have a relatively high density, but the liquid still tends to form to the shape of the container, and then usually it still will actually flow. If you had a supercritical fluid that you can almost like spill it, and then eventually it'll expand into a gas. But for a moment, it would look like a liquid. So it just becomes a substance that's hard to classify if it's a gas or a liquid. So our critical point is just the temperature and pressure beyond which we couldn't classify the substance as being a pure gas or a pure liquid. But if you're below this point, this way, then you're a gas, and if you're below it this way, then you're on the liquid side. Another interesting point is the triple point. So a triple point, in terms of definition, it's the coexistence point, or it's the point at which you have all three phases of gas, liquid, solid in equilibrium with each other. But one of the things that's really interesting with a triple point is that it's not usually at a very low pressure. It's usually at like a fairly ordinary pressure, where if you go below this point, then you can only have transitions direct from solid to gas and gas to solid. So it kind of says that there's going to be a lot of regions in pressure temperature where a solid can't normally melt and then turn into a gas. It has to directly go to the gas phase. So some compounds like naphthalene, we use it in mothballs, it's a solid. Sometimes you put it in your garden. Rodents tend to pick up the smell and avoid going into your garden. But naphthalene is a solid compound that goes direct to the gas phase. So it has its triple point above standard pressure, above standard temperature, so that at normal temperatures, naphthalene sublimes directly to the gas phase. And so there's a lot of substances that will undergo sublimation events. It's just as long as you're at a pressure below and temperature below the triple point, then that sublimation event can take place. And so triple point, again, the coexistence of the three phases, but below it, you then have the possibility of direct sublimation solid to gas. And if you're at then a pressure above the triple point, so think about a sample that's held at a constant pressure. That's like an ordinary sample. You could think possibly something at 1 atm, standard pressure. So at 1 atm, and this is the phase diagram here for CO2, for carbon dioxide. So at 1 atmosphere, CO2 has a sublimation event, a gas to solid. Dry ice, solid CO2 sublimes at about minus 78 degrees C. So if you've ever seen dry ice, you probably noticed that it goes from solid, you never notice a liquid, and it ends up disappearing. It's disappearing because it's forming its gas, its vapors, and it's doing so at 1 atm through the sublimation event. And so then if you go to a higher pressure and hold the sample at some higher pressure, maybe in some sort of pressure cooker, maybe in some sort of a vacuum system, or the opposite of a vacuum system, some system that can supply pressure, you can then have the CO2 melt into a liquid phase, and then the liquid could then boil into the gas phase like you expect most liquids to do. Like water does this, so this vapor pressure diagram is for water. So at 1 atm, we know water goes solid to liquid, and then liquid to gas, and undergoes the kind of normal process of those phase changes. Water's triple point has a particularly low pressure, so if you go to a really low pressure and go beyond this temperature here, so it's a little bit above 0 degrees C, but if you go below this pressure, then ice can undergo a sublimation event. But you just have to go to a particularly low pressure in order to see the direct solid to gas transition for that substance. And so then another detail that's kind of interesting is the nature of this curve here. That's the melting point curve. And so waters, I'm going to expand this a little bit here. If you take solid water that's really close to its, say it's close to the melting point, and then you apply a pressure. So if we apply a pressure, we can actually you go like straight up. Applying a pressure is kind of thinking of, change the pressure on the x-axis, so hold the temperature constant, and then imagine going up and down as changing the pressure. So if we took a water sample that's ice and applied a pressure, you can think of this as just a mechanical, physically pressing down on something really hard. Maybe you have a some sort of a mechanical system to help supply this force, so it's not an actual handheld piston. Maybe it's a hydraulic of some sort. But if you apply a pressure to solid ice, it actually turns into a liquid. And so you can actually liquefy solid ice by applying a pressure. Now, what does that mean? Well, that means that water liquid's density is greater than the density of solid ice. That's just a consequence of as we take solid ice, if you increase the density, if I push the molecules closer together, that's reducing the volume but keeping the mass constant. So that's increasing the density. So if I increase the density going upward, so what I'm doing here is increasing the density by applying a pressure, because I'm just pushing the atoms closer together. I then increase the density. I then see that the liquid has a greater density than ice. Now we know this, ice floats on water, and that's why it floats on water, is because it has a lower density. But we're seeing that kind of bear out in the phase diagram. Now, most substances, like if I took CO2 and I take, liquid CO2, apply a pressure, it's kind of hard to go straight up. But if you go straight up, it's going to form a solid. Most liquids, if you apply a pressure, solidify. So it's kind of abnormal that water has this property. So it's abnormal for the liquid phase to have a greater density than the solid. Most substances are the other way around. If you apply a pressure to the solid, it stays solid. If you apply a pressure to the liquid, it turns into usually the solid. So most gases, if you take a gas at some set of conditions, you can usually liquefy or solidify depending on what particular temperature the gas is at. So you can take gases and you can either deposit them by applying a pressure or turn them into liquids, vaporize them by turning them into, condense them by turning them into a liquid. Okay, so another detail is that the critical point has a relationship in triple point 2 usually to intermolecular forces. The stronger the force, so sometimes you see a relationship that water has strong intermolecular forces, so it has a high critical set of points. CO2, weak intermolecular forces, lower critical points. Okay, so the phase diagram shows you temperature change left to right, pressure changes up and down, and then thinking density up and down with pressure changes, and then just thinking what phase changes take place when we generally change temperature left to right. Okay, our last slide for chapter 11 actually comes out of a section we don't cover for the exam, but I just wanted to mention this from this final section. I think this is a neat kind of topic in the last section of the textbook. Most soaps are very interesting. They usually have some sort of a group that has a very strong intermolecular force of attraction, usually something like this particular group here. That's called like a carboxylate. And what that gives you is an ion dipole force of attraction on the soap molecule. So that has a very strong interactive force with water. So water is very attracted to this group here because of the ion dipole force of attraction. And so then this tail here, the molecule has a very long carbon chain attached to it, because if you want to have a soap, you need like two properties for a soap. It has to dissolve oils, and then it has to somehow solubilize them so they go down the drain. Otherwise, if you just had a soap that only had the hydrophobic end, the water-hating, the grease-loving end, then you would just grease up whatever you're trying to wash away, and it wouldn't actually go down the drain. So you need something that turns like an oil droplet into something that's water soluble. So we just take the chains that have a water hating end, an oil loving end, and then a water loving, a hydrophilic end, a group that really has a strong intermolecular force with water, and you end up forming these droplets. So you can make an oil droplet water soluble through using something like a soap or a detergent. So I just thought it's useful to kind of see that we sort of combine the kind of two main functional groups. One is the really water attractive part, and then the other end is the oil attractive part. We just put them together onto one molecule. And so that's kind of how soaps are designed and used. So I thought I would point that out. Okay, so let's get into some chapter 10 review to kind of go back and look at some chapter 10 topics. I think eventually we'll circle back into some chapter 11 review too here today. But which of these gases has the greatest density? Now, when you see a question like this does take us back in time a little bit, so we may have to remember a few equations. And we can either check an equation chart, but I'd rather kind of think, okay, what equations do I probably remember from chapter 10? I probably remember this one. And if I rewrite this as N is PV over RT, I can then maybe say, okay, mass over molar mass can be my moles. So if I take mass over molar mass, I can rewrite that as a relationship that's just the same. N is equal to PV over RT. M over V is density. So if I move the density to this side of the equation, put the molar mass over here, I can then write that M over V is equal to pressure times molar mass over RT. And then this, of course, is density. Now, there might be an equation on your sheet. I think it is on the final packet. I'll be releasing the final exams probably later today if you wanted to take a look at the practice final materials. We haven't covered chapter 12 yet, so the chapter 12 topic, you may want to wait till lecture on Monday. We'll talk about that last chapter on Monday, and then we'll spend our last lecture on mostly review topics. But I'm just kind of coming up with this relationship here that pressure times molar mass over RT is related to my density. So when I'm looking at my options here for density, the first thing I could have done was just made an educated guess and thought, okay, maybe the heavier gas at the higher temperature. So maybe I'm kind of thinking, oh, maybe it's this answer here because it's the heavier gas, it's the higher temperature. But let me think about how my density equation kind of looks, because I'm dividing by the temperature. So I actually want the gas at the lower temperature, not the higher temperature. So if I take two gases, if I take the comparison of, let's say, the two propanes at the two different temperatures, under the two temperatures, 5 atmospheres at 298 K, that's going to have more gas. I'm going to have more gas in that gas cell to create that pressure. If I increase the temperature of that, so if I take the gas in B, so I have this 5 ATMs of propane at 298 K. If I just take whatever that gas is and increase its temperature to 348, what happens to the pressure? It would go up by the Boyle's, or yeah, I think that's Boyle's law, P versus V. So if I increase the pressure, I'm going to increase, if I increase the temperature, I'm going to increase the pressure. And so then to get back to a pressure of 5 ATM, I'm going to have to let some gas out. So I'm going to have to lose some gas in the container. That's going to lower the density inside the container. So I want the gas at the lower temperature. That's going to have the greater density. And then if I look at my molar mass, of course, I want a higher molar mass. So I'm going to choose the gas here at the lowest temperature of the greatest molar mass, so that would be B. Now, if we wanted to, we could go plug in numbers and calculate the actual densities here. I'm not going to bother with that, but if you wanted to, you could go through and actually calculate the densities of each of those gases and see that B should have the highest density. Okay, so a problem here that gets us into a couple equations from chapter 10, a few ideas of the ideal gas law, hopefully gets us remembering some of those equations if we haven't used them in a while. Let's take a look at this question here. 2 liters of gas at constant pressure. We have a movable piston that's going to, if the pressure changes, maybe keep a constant pressure. It's going to expand against the atmosphere. So we're at 25 degrees C, then we cool the gas. So maybe the thought is I have some sort of a container that just has a movable lid of some sort that's just pressurizing against the atmosphere. So the pressure inside here is just atmospheric pressure. So if I take this and maybe put it into an ice bath of some sort, so maybe I take this gas, put it inside of a container. I think it's nice to have an idea of how do you change the temperature of a gas sample. Well, it could be that it's a balloon and we just put the balloon in a cold water bath. Maybe we have a container that has some sort of movable piston and we put it into some sort of a cold bath. And so then the temperatures drop to negative 25 degrees C. What's the new volume of the gas sample? So we're initially at 2 liters, then we cool it. What's the new volume? Well, so let's see here. So if I look at PV is equal to nRT, and I'm keeping the pressure constant, and I'm keeping the moles, the amount of gas. It's a sealed container, so the amount of gas is constant. So it's my V over T that's changing, and V over T would be equal to NR over P, but these are all going to be held constant. That says constant. Let me rewrite it. So meaning that all of these values here are not changing during this changing of the temperature. And so what that allows me to write is that V1 over T1 is equal to some constant that's equal to the same constant for V2 over T2. So it's like V1 over T1 is equal to a constant, then I change my temperature, change my volume accordingly, it's equal to the same constant. So it's equal to the same NR over P. So V1 over T1 is equal to NR over P. If V2 over T2 is equal to NR over P, then they're equal to each other. This is also from one of the laws. Charles' law, I think, is what this one is. And so you may remember this equation from one of the laws that we went over too. So there's a couple ways you might get at this equation here, but one of the key details is I got to really track the temperature in the proper unit. If I'm solving for my V2, which would be equal to V1 T2 over T1, just doing the arithmetic there, that if I do the negative signs, it's going to really give me a screwy answer. So if you're thinking, okay, 25 negative divided by 25 positive gives me negative 2 liters, then of course that's wrong. We're not going to like negative volume when we change the temperature. So we just have to go to absolute temperature in this chapter. So we're taking our 2 liters initial and then times our T2, negative 25 is negative 25 plus 273. That would be, I think, 248. Double check. Yep, 248 Kelvin. So I'm just taking negative 25 degrees C plus 273 to convert over to Kelvin, and then dividing by my initial temperature, 25 degrees C of 298 Kelvin. And of course, I should expect the volume to decrease, and it does. It decreases to 1.66 liters. So gas law question relating volumes and temperatures here and deciphering that information that we can apply this equation, figuring out how to write the equation from a few different angles on how we can get to this equation, and then just plugging in the math, making sure we convert to Kelvin. So we have a gas with an initial pressure, volume, temperature. We're calling those P1, V1, and T1. What's the new temperature of the gas when its pressure is tripled, but its volume is cut in half? And so I have some initial temperature. And then, so this container must be keeping a constant number of moles, so we're not changing the number of moles. So if I move my T1 over here, then my P2, V2 over T2 are going to equal the same N times R constant. And so therefore they're going to equal each other. So we're just changing the pressure, volume, and temperature, and they have to maintain this relationship. Otherwise, the moles of the gas would have had to have changed. So in order to keep the moles of gas constant, these two equations have to be equal to each other. And so then what we're doing here is we're taking P2 and changing it to 3 times what it initially was. And so when it says the new temperature is triple, so T2, oh, I cannot read today. It says, what is the new temperature when the pressure is tripled? So P2 is tripled from P1. And then the volume is cut in half. And so I can plug those in to my equation. Let me see if I can. Oh, okay. I'm not clever enough to move this out of the way. Let me rewrite that over somewhere that's not in the way where I'm trying to write. So P2 is 3 times P1, V2, 1/2 V1. And so I just want to write those in here. So my P2, 3 times P1 times 1/2 V1, and then divide by T2. Okay, and so let me then say that this is equal to P1 V1 over T1. And so I'm trying to solve for T2. So let me multiply T2 over to this side here. And then let me multiply T1 over to this side here. And then divide both sides by P1 over V1. So let me rewrite this. So 3 times P1 times 1/2 times V1 times T1 would be equal to P1 V1 times T2 so far. And so I'm going to divide both sides by P1 V1 to cancel those out here. And so my P1 cancels, my V1 cancels, so my T2 equals 3/2 times T1. So which looks like this answer here. A lot of algebra steps here. The key is kind of taking in that information that we're tripling the pressure. So my P2 is just 3 times P1. My V2 is 1/2 of the initial volume. And I'm just plugging those in here and then solving for T2. Now, one thought could be, you could throw numbers in. If you get this problem on a test and you're like, information overload, you can be like, well, why don't I just make up pressures and just see what happens? It's just like, put in a pressure, volume, and a temperature, and then triple the pressure, cut the volume in half, and then just see what the new T2 is equal to and what the relationship is. So a thought could be, if I just got to throw numbers into this, I could probably just pick whatever random V, pressure 1, V1, and then T1, and then just change them accordingly and see what happens at T2. So that's another way you could just throw some numbers into this problem if you happen to get stuck on this. But this is a tricky problem because it involves the relationships of 3 of the sort of parameters of our gas, where the fourth one, the moles, are being held constant, and then coming up with that relationship. So I think if you get to this equation here, that's like half the problem. And the other half is seeing how we can just plug in the new P2 and V2 and then use algebra to solve for what we're looking for. So one thought too is just try to keep track of what it is you're looking for. If you get in a problem like this and you're stuck, one thing I'd say is a good test taking strategy is save the hard problems for last. If you get a problem like this on the test and you're like, this is tricky, I don't know exactly what to do, maybe save it for last so you have a couple minutes, hopefully at the end of the test, to devote to this problem, and then just keep track of, okay, we're looking for T2, so that we know what it is that we're looking for. Sometimes in a problem when we get lost and we're not sure what to do, sometimes we lose track of what we're looking for. Okay, so let's take a look at the problem down below. So the molar mass of a gas with a density of 5.66 grams per liter at the given temperature and pressure. And so this problem here looks like it's going to come back to that same equation we were using on our first problem, that our M over molar mass was equal to PV over RT. And so again, if we rewrote this as M over V, that's equal to pressure times molar mass over RT, and that this, of course, is density. So we have density is pressure times molar mass over RT. Now again, pretty certain this equation is on your equation sheet. But if you understand where these equations come from, they're in your mind, you know how they relate to each other, you can sort of probably come up with these relationships or know kind of, okay, this is just going to be some sort of ideal gas law problem. It's going to be a problem that just relates the M over molar mass and the units for moles, and then does some rearranging. Okay, so I'm going to solve here for my molar mass. Just have to account for some units here. So I want to know the molar mass, so I'll solve this equation for molar mass. So my molar mass would be equal to density times RT over the pressure. Just taking this equation here and solving it for the molar mass. So let me plug in my density. And again, showing units is usually helpful. We'll catch mistakes this way. I'm going to use my usual units of my gas constant. There's probably only 2 units of R that would be given on the test. The most commonly used units are the liter atmospheres per mole Kelvin that we're using here, and then the joules per mole Kelvin, which rarely do we use for any problem in chapter 10. We use it for calculating like gas velocities, but that problem mathematically isn't all that exciting. So you probably won't see any calculations with any other unit of R but this one. If you had used in the past either the liter torr per mole Kelvin unit and you looked it up in the book, that probably wouldn't be on the test. So we're just gonna have to change our pressure into ATM here. So we're just gonna have to make sure to convert our pressure into the proper unit. To multiply by temperature, 35 degrees C is 308 Kelvin. So our Kelvin cancels, our per liter and liter cancel. Then I'm going to divide by 745 millimeters of mercury, and then just know that I have to convert millimeters of mercury into ATM. So my ATM cancels. And then my units left over here should be grams per mole. So I get the proper units of molar mass. I get 146 grams per mole. Now, one thought is denominator. Probably want to throw parentheses around that to make sure that we get that math correct so that we're not making a mistake and multiplying instead of dividing by 760. But, and then other than that, tracking units in these problems. But this is how we can find molar masses. So if you have a gas sample, you don't know what it is, you can figure out its molar mass. The key detail here is you have to have a pure gas. It doesn't really work for a mixture. So you need a pure gas. If you know its pressure and its temperature, its density, or it's the volume or the mass of the gas, you can then relate that back to the molar mass of the sample. So air is a mixture, 21% oxygen, 78% nitrogen, 1% argon, and everything else has a pretty low percentage, like a lot of water vapor, some CO2. We're asked, what is the partial pressure of oxygen in a 1.00 ATM sample of air? So this is, standard atmospheric pressure. How much of that pressure is due to the O2? Well, this is using Dalton's law of partial pressures. So Dalton's law of partial pressures is that the partial pressure of a component is just equal to the mole fraction of the component times the total pressure. And so this is like partial pressure, the pressure of just like the O2, and then this component here is the mole fraction. But if you look at the ideal gas law, N is proportional to V. So if we have the volume percentage, the percent by volume, that's proportional to the mole fraction as well. So this would also be the mole ratio. So because N and V and pressure all have this relationship from the ideal gas law to each other, it's also the pressure ratio. The gases are all at a constant temperature, so the temperature ratio is kind of boring because all the gases in the mixture are at the same temperature, so there's no real ratio of temperature. So the temperature itself is what's constant for all the substances within the mixture. But then the only thing that is not is the mass ratio. So the mass ratio just depends on the given molar masses. So the mass ratio, like if you looked at the volume percentage of air, the mass percentage would be different. So the percent by mass of air would not be 21% oxygen, 78% nitrogen necessarily. So it's just the relationship of the moles, the volume, the pressure, because those are what are directly proportional to each other within the ideal gas law. And so, but with the equation, all we need to do is use the mole fraction of O2, which would be 0.21, the same as its volume percentage. So just the percentage just expressed as a fraction. So I'm just using this number here to get the 0.21. And so I'm then multiplying that by 1.0 ATM. So the partial pressure of oxygen and air is about 0.21 atm, nitrogen 0.78 atm, argon argon about 0.01 atm, water vapor 0.004 atm, etc. So the partial pressures are just the mole fractions times the total pressure. Now if we had some other pressure, like if we're at an atmospheric pressure of 253 millimeters of mercury, I guess that's typical pressure on Mount Everest, then what's the partial pressure of oxygen? At this condition here, well, it would be equal to 0.21 and then times 253 millimeters of mercury. So the partial pressure of O2 would be equal to the same fraction. So the air composition is the same at high elevation. So the composition of air is predominantly still 21%. So we're still subject to this composition of air, not really changing at elevation. And so we have roughly the same percentage of air, now 253 millimeters of mercury. Instead of 1 atm, it's going to have a lower pressure of only 53 millimeters of mercury. So let's convert that to atm to compare to above. That's only 0.070 atm. So a lot lower pressure, partial pressure of oxygen at high elevation. It's going to be harder to breathe, so anytime you've been in like Denver or somewhere at high elevation or in the mountains, you probably find that if you're hiking, you have a harder time, especially when you first get there, getting used to it, breathing, just because there's less oxygen in the air. So you're taking in less O2 with each breath. So that, is probably something you've experienced, or if not, you probably will at some point and understand that's why. Let's talk about mixing gases. So this problem here is looking at, we have a gas cylinder of nitrogen. We have some sort of a valve. So imagine this valve is closed between the two gases. So we have gas 1, gas 2, some sort of valve between them that's not open. We have oxygen on this side. And then we have the two gases under these sets of conditions here, where we have 2 liters of nitrogen. So this bulb here is about 2 liters, whereas the oxygen bulb is about 3 liters. We have a little bit higher pressure, well, double the pressure of O2. We have 2 atmospheres of oxygen in its container. We have 1 atmosphere of nitrogen in its container, and they're both at room temperature, 25 degrees C. Well, what's going to happen when we open that valve? When I open the valve, the 2 gases are going to exchange. And predominantly the higher gas is going to expand into lower gas, but they can then move into each container and expand into each new volume. So the nitrogen can expand into the oxygen volume, the oxygen can expand into the nitrogen volume. So when we open the valve, the volume for each of the gases changes to 5 liters. So each of the gases then has 5 liters to distribute into instead of just the 2 versus the 3 liters. And so what's the total pressure when we open the valve? Well, I've seen this a lot of times where students are like, oh, it's either got to be 3 atmospheres or it has to be the average of the 2 or something. We have to think almost of the 2 gases expanding and then how that relates to the total pressure. So our total pressure would be equal to the partial pressure of the O2 plus the partial pressure of the N2 once we allow the expansion to take place. So if we recalculate our oxygen pressure into the 5 liters, the nitrogen pressure into the 5 liters, add those 2 up, that's my total pressure. So the idea is individual partial pressures just sum up to the total pressure. So that's the first thought. And then the other thought is that when I expand this to 5 liters, the pressure is not going to be 1 atm anymore. So I need to kind of do a P1V1 equals P2V2 expansion for the O2, do the same thing for the N2. Excuse me. So let's think for the nitrogen. It's going to go from a P1V1 equals P2V2 and expanding from its initial volume of 1 liter in the 1 atm, and then it's expanding to now 5.0 liters. And so the P2 for the N2 would be equal to the P1V1, and then dividing by my new volume of 5 liters. So the nitrogen pressure should drop when it expands into the new volume. I can do that math in my head. That's 0.40 atm. So that's my nitrogen pressure once it expands into the new volume of the oxygen side. And then I do a P2V2, or a P1V1 equals P2V2 for the O2 from the initial volume of 3 liters and 2 ATM into the new volume of 5 liters. So my my P2 for O2 will be equal to 2 ATM times 3 liters divided by 5 liters. 6 over 5, I think that's 1.2 ATM. So these pressures are dropping because of the expansion. So even though we have a relatively high pressure of both of these, they expand and lower their pressures through expanding into the volume of the other gases. And remember, the two gases don't care that the other's there. They just see the new volume. So that the one gas is like, oh, I have new volume to expand into, so it does. The other gas, oh, I have new volume to expand into, so it expands as well. And through that expansion, their pressures are dropping. And so then my partial pressure of O2, 1.2 ATM from over there. And so that gives me a total of 1.6 atmospheres. So it's kind of like a weighted averaging, but it's just a double expansion. So the two gases just expand into the other volumes and it becomes a summation of the partial pressures. So partial pressures of two gases, the oxygen doesn't care that nitrogen's there. The two pressures are just simply additive. Remember, gas mixtures are non-interacting particles. We could do this problem a few other ways. We could have said we have the pressure, volume, temperature. We could have calculated the moles of nitrogen in the one container, right, just from PV is equal to nRT. Would have taken maybe a little bit longer, but we could have calculated the N of N2. So I could have said an alternative approach would be, well, how many moles of N2 are there? I could have said, well, how many moles are there of O2? And then I could have summed those up. That's my total number of moles. And then I can relate that back to PV is equal to nRT and plug the total moles in the new volume of 5 liters and that temperature still at 25 degrees C. So there's a few ways within gas law problems. There's usually a few ways you can get at the solution. So don't always feel like there's one way to solve these problems. If you were thinking, well, why don't I just solve for the moles and add them up and then plug those into the PV is equal to nRT, hey, that works too. Let's take our attendance here. We'll still do another problem or two. We still have about 7 minutes to go. So Mendeleev is our keyword for today. Okay, so Mendeleev again, if you missed the keyword. So let's recall the van der Waals equation from the end of chapter 10. Now this equation, like we could plug numbers into this, and like I used to, and it's kind of a fun equation in a way to plug numbers into for an example. It's not fun to do that on a test because there's obviously a lot of different math that goes into this equation. And so for relatively short exams, we tend to avoid doing the arithmetic. But the one thing that's interesting is that the volume problem has a correction that introduces an error that kind of goes one way, and then the pressure problem has a correction that goes the other way. So we have like pressure being lost due to intermolecular forces that we're re-adding into the equation. That's why there's a plus sign here. So we're losing pressure due to intermolecular forces that we're then like throwing back into the equation to try to recapture or to understand. And then we're also then realizing that our assumption that the gas particles occupy a negligible portion of the container breaks down, especially at high pressures, because at high pressures, the amount of gas in the container is really high, and the actual free space is smaller than the volume container. So the V minus NB is a way to try to calculate our free space and to correct for the assumption that the gas particles don't occupy volume. So it's kind of subtracting the space occupied by the matter in the container. So we're just trying to correct for intermolecular forces with the A term, and then correct for the volume problem, the space occupied by matter problem with the B constant. Now, so A is related to strengths of intermolecular forces, which now in retrospect from chapter 11, I think we have a better perspective now that strengths of intermolecular forces for comparably sized molecules increases with dipole-dipole force. It increases with the linearity, or like more atoms, the better. So if we have 100 grams per mole, it's better to have a bunch of atoms for strong intermolecular force. It's better to have a linear connection of atoms as opposed to a branched set of atoms for stronger intermolecular forces. It's better to have hydrogen bonding than no hydrogen bonding. It's better to have a dipole-dipole force and no dipole-dipole force, those sort of considerations. But now if you're trying to get the gas to behave ideally, you would say, oh, well, let's make it a single atom, because then your single atom, like a noble gas, would have the smallest A value for a comparable size. So at least now we have a pretty good idea of what it means to have comparable or different intermolecular forces and how to relate those. And then B is just the size of the molecule, or the size of the matter that makes up the compound. And so B is just related to like the density or the size. And so again, having more mass is better, and even having multiple atoms is better too. So one single atom has a smaller volume that it occupies than having the same mass spread out. So we have a little bit of a linking of what A and B are related to some extent. But if I'm looking at like, and one of the comparisons here is for CH4 versus water in terms of the A value. Let's look at that first. So the intermolecular force of water, we have the hydrogen bonding capabilities. CH4 doesn't have hydrogen bonding, it's nonpolar. And so A is going to have the larger A value because it has stronger intermolecular forces due to the hydrogen bonding. So not too surprising here. We could have compared their B values. I kind of wish I asked us to compare the B values, because water ends up being a little bit smaller though, because water compared to CH4 only has this. I know we write the electron pairs here, but there's really nothing there in terms of space. Carbon has atoms there and ends up having a larger size. So, and we can compare this on the next slide. We can look at the B value. I expect that the B value of CH4 would be a little bit higher, just due to the fact that CH4 is going to have the 2 extra atoms, should occupy a little bit more space. So the next slide will have a comparison of these values so we can take a look and see if our predictions are correct. And then if I'm comparing the B value, the size of the molecule, well, obviously having a double bond to oxygen versus throwing an extra carbon into the mix, that adding the extra carbon should add to the size. The CO2 should be bigger, take up more space, so it has an extra atom. And it has a larger molar mass too, so the B value of CO2 should be higher. Okay, so water should have a higher A value, more polar, but probably smaller B value than CH4. And then if we're comparing CO2, should have the bigger B value, and they're both nonpolar, but CO2 is bigger, so CO2 probably also has the bigger A value. So let's take a look at these two. Let's look at water versus CH4 first. The A value of water, bigger than the A value of CH4, just like we predicted, because it has that intermolecular force, so that checks out. And then I mentioned that CH4 probably takes up more space because it has the 2 extra bonds that water doesn't have, and we notice that the B value is bigger, so that makes sense. So the two things we were looking at for water versus CH4, check out. And then what about O2 versus CO2? So that's this comparison here. So for O2 versus CO2, let's look at the B value first. You see that CO2 is indeed bigger. So it takes up more space. So the B value of CO2 is bigger. So that was correctly predicted. And then the A value, CO2 is bigger, has more dispersion force. So it has a stronger intermolecular force. So that checks out too. Okay. So again, don't expect math with this equation. We didn't even go over the math, but just think about just relating the A and B constants to molecular properties and trends. Yeah, so let's save this. I'm looking at the time, going, this is a busier slide than we probably want for 8:54. So we'll pick up from here. The rest of the packet goes over some chapter 11 stuff too. So we'll get into some chapter 11 review, talk about chapter 12, and then get into some final exam review after that next week. All right, guys, have a great weekend. Enjoy the game Saturday. Go Buckeyes.